All right, continuing on. So if I wanted to convert 240 degrees, I'm going to do it in the exact same fashion. I'm going to go 180 degrees is equal to 1 pi radians. I want to calculate what 240 degrees is. Multiply and divide 240 pi over 180. I'm going to use my calculator and simplify this. And when I do that, this simplifies to 4 pi over 3 radians, which equates to 4.19. Okay? All right, convert the following radians to degrees as to the nearest degree. Okay? Now we're taking a radian exact value and we're going to change it back to degrees. So again, we're going to start by saying 180 degrees is equal to pi. I want to figure out what pi over 2 radians is equivalent to, question mark. So I'm going to take 180 times pi over 2 divided by pi. So what's going to happen is that these pi's will end up canceling. 180 divided by 2 leaves me with 90 degrees. Or you can say, well, if 1 pi radians is equal to 180, a half a pi is going to represent half of 90. Okay, so same thing with 3 pi over 2. I'm going to go 180 equals pi over 2 pi over 3. We're going to cross multiply, divide. Pi's cancel. I'm going to multiply 180 times 2 and then divide by 3. So this should equate to 120 degrees. And then lastly, 180 is equal to pi over 3 pi over 2. Cross multiply and divide. We're taking 180 times 3 pi over 2 divided by pi. I multiply, our pi's are going to cancel. 180 times 3 divided by 2 leaves me with 270 degrees. Okay, so that is how you convert from one to another. Okay, we often work with angles of 30, 45, and 6 degrees, and then multiples of these from 0 to 360. So we're just going to identify these angles within the into both degrees and radians as we rotate around the circle, because this is the start of our unit circle. Okay, so we already know that this is 0 degrees, this is 90, this is 180, this is 270, and this is 360. We want to start to almost memorize these values as we go around. Okay, all of these ratios are basically going up by 30. So this would be my 30 degree angle, this would be my 60 degree angle, 90, 120 degrees, plus 30 is 150, plus 30 is 180, plus 30 is 210, plus 30 is 240, 270, 300, and 330. Okay, so those are all of our angles of multiples of 30 and 60. Now we're going to do multiples of 45. So this would be 45, 90, 135, 185, 270, and 315 degrees. Okay, so now we want to just start to get an idea of how to get these radians going. Okay. So if we start off with a 30 degree angle, if we started just by converting this from 30 degrees to radians, we would get a ratio of pi, or a fraction of pi over 6. So now to write the radians of every 30 degree multiple around, you can literally write everything over pi over 6 and simply count your pi's by adding 1 pi over 6 each time. So 6, this would be 2 pi over 6. But technically, 2 pi over 6 would simplify to pi over 3. This is 3 pi over 6, but simplifies to pi over 2. This is 4 pi over 6, but simplifies to 2 pi over 3. This would be 5 pi over 6. This is 6 pi over, simplifies to half a pi. This is 7 pi over 6. 8 pi over 6, which simplifies to 4 pi over 3. 9 pi over 6 simplifies to 3 pi over 2. 10 pi over 6 simplifies to 5 pi over 3. 11 pi over 6. And 12 pi over 6 would simplify to just 2 pi. All right, now we're going to rotate our 45-degree angles. Okay, so if this is half a pi, then 45 is going to be a quarter pi. And we're going to count quarter pies around now as well. 1 quarter pi, 2 quarter pi, 3 quarters of a pi, 4 quarter pi, 5 quarter pi, 6 quarter pi, and 7 quarter pi. So that's a quick reference, a way to get all of your angles around your unit circle. All right, example 5. Draw the following angle or terminal arm given and convert your answer from given units to determine the reference angle. Okay, so 150 degrees. Okay, we are going to sketch this. Here is 150. Okay, my reference angle should be 30 degrees. Because 180 minus 150 would give me 30. Okay. In radians, right, that radian reference angle would be a 30-degree pi over 6. And my rotation in radians would be a 5 pi over 6. Okay. All right, pi over 6 radians, fairly straightforward, equivalent to this 30-degree angle. Right, so my reference angle is also going to be pi over 6, or 30 degrees, and my rotation in degrees would be 30, because we're working in the first quadrant. Negative 60 degrees. All right, so if I'm going to rotate in the negative 60-degree rotation, that reference angle would be a positive 60 degrees, which relates to pi over 3 radians, and the rotation will be a negative pi over 3 in radians. Okay, and then lastly, 2 pi over 3 radians. It's here, right? My rotation is 2 pi over 3. My reference angle would be this rotation here. Okay, so if I were to find my reference angle, I would take 1 pi and subtract 2 pi over 3. So then you have to start using fractions. How do you subtract fractions in order to subtract this? I'd have to get a common denominator, so this is going to change to 3 pi over 3 minus 2 pi over 3. My reference angle should be pi over 3 radians, which is the same as a 60-degree angle. My reference angle, or sorry, the rotation angle in degrees, using my circle from up top, works out to be 120 degrees. All right, moving on to coterminal angles. So coterminal angles are angles that have the same location of a terminal arm. Coterminal angles do not have the same value, however. So 90 degrees is not coterminal with pi over 2, because even though they have the same terminal arm, they're essentially the same angle. So coterminal angles are locations that literally have the same terminal arm. So find 2 angles that are coterminal with the example given in the same units. So whatever units I'm working in, you want to stay in those units. So I'm going to start with a negative 5 pi over 6. Well, negative 5 pi over 6 means I'd want to rotate in this direction. Okay, so here's 1, 2, 3 pi over 6, 4 pi over 6, 5 pi over 6. Here is my rotation, and it's a negative rotation. So a coterminal angle to this could literally be any other angle that ends up with this same. So one possibility is, rather than rotating in the negative direction, I could rotate in the positive direction, and this would be a coterminal angle. And if I rotated in this direction, this angle would give me a positive 7 pi over 6. Another possibility is, well, I could rotate a full circle, which is 2 pi, and then back around to here. So another possibility is I could add a full rotation to my 7 pi over 6, which would give me 19 pi over 6. This would be another coterminal angle. Or I could have wrote full rotation in the negative direction and added the negative 5 pi over 6. So negative 17 pi over 6 would also be coterminal. All of these answers would be correct. Everybody would have potentially a different coterminal angle. All right, question B, 5 pi. So if I rotate, I'm rotating positively, so this would be 2 pi. Another rotation would be 4 pi, and then 5 pi would bring, so this is the sketch, it's like a spiral, to here. This would represent my angle. So what would be a coterminal angle to this? Well, a coterminal angle is getting to this location of pi. Well, so pi would be a possibility. Rotation plus this, that would be a 3 pi. Or I could have gone in the negative direction. Negative pi, negative 3 pi, lots of possibilities. Okay, so remember, we're getting to that same terminal arm, but we're rotating either a full rotation plus adding, or we're rotating in the opposite direction. So if I gave you the angle of 40 degrees, okay, if I rotated in to get to there, this would give me a coterminal angle of negative 320. Or I could have added went a full rotation and back, which would be 360 plus 40 would be 400. Okay, so two possibilities. And then negative 430. Well, negative 430 is bigger than 360, so I'm doing a full rotation, which is 360, and then I have 70 left to rotate. So there's my rotation. So a possibility is I could just rotate to here, which would be a negative 70. Or I could rotate just to here with a positive. So 360 minus 70 would be 290. So two possible rotation angles, coterminal angles. All right, if a given angle of angles coterminal with it, one expression can represent all those locations. So technically, if I were to go back to this, well, let's start with the 40-degree angle. A little bit easier to work in degrees still. If I started with this angle, I could rotate this way, or I could rotate this way. But I could also do a full rotation, come back to this. I could do 2 full rotations and come back to this. I could do 3 rotations and come back to it. 4 rotations. I could technically be rotating around forever and ever and ever, as long as I'm getting back to this terminal arm. So how do we express that angle as just a general expression, as opposed to having to write all of them out, which you would never be able to do because there's an infinite number of them. So technically, what are we doing? We're starting with our reference angle, which is 40 degrees angle, and I want to add a full rotation to that, which is 360. But how many times do I want to do that? So I'm going to multiply this by n times, and I'm going to say, but technically I could add 360 each time, or I could subtract 360 each time to give me my negative angles. So I want to denote n as being part of our integers, because our integer values will allow this to add or subtract 360 and over again. Okay. Okay, what about negative 430? Right? So this would represent, so what we want to do is we want to use our positive rotation angle, is always easiest. So back to this negative 40, our positive rotation was 290. And then I'm going to just add a full rotation to this n times, where n belongs to the integers. Or you could write this as 290 plus or minus 360n, but in this case you'd say n would have to belong to the whole numbers. Because you're adding or subtracting this, we no longer want this to belong to the integers, we now would want it to belong to the whole numbers. Okay, and then how would we do this with radians? Same idea, we're going to take our positive rotation angle, which is 7 pi over 6. We're going to add 2 pi, because that's a full rotation in radians, times n, where n belongs to the integers. So same sort of idea, we're just working in radians now. Okay, my positive rotation angle is pi, or instead of this belonging to integers, we could have this belong to our whole numbers. So this is another possibility. Okay, and you might see both potentially expressions on an exam, so you have to recognize both of them. Okay, the last thing about today is arc length. Okay, radian measure is the ratio that compares the length of an arc of a circle to its radius. So technically, 1 radian is the measure of an angle subtended at the center of a circle by an arc equal to the radius of the circle. So at the point when the radius of a circle is the same length as the arc length, this angle will measure 1 radian. Okay, so when the arc length equals the radius, the angle measures 1 radian. Okay, so just another definition of radians. The arc length of a circle describes a portion of the circumference of a circle. So technically, right, all the way around would represent the circumference. The arc length is just representing a portion of that. So how do we find arc length of a circle? A is equal to over or theta times r, where theta must be in radians. So this is key. Okay, so it has to be in radians. So an example, determine a circle with radius 6.7 centimeters and a central angle of 130 degrees. So if I were to sketch this, this angle in here is 130. I want to find the arc length, and the radius is 6.7. So in order to find my arc length, I'm going to take my angle, 130 degrees, but I can't use this angle unless it's in radians. So I have to convert my angle to radians by setting up a ratio, and I want to generally try to leave things in exact values. So I'm going to go 180 degrees is equal to pi over 130 equals, so I get 130 pi over 180. Okay, so that angle simplifies to 13 pi over 18. So this is the angle you should be using in your formula. So I'm going to take 13 pi over 18, and I'm going to multiply that by our radius, which is 6.7. And we'll round this to the nearest tenth. We get an arc length of 15.2 centimeters. Okay, B, determine the central angle for an arc length of 13 centimeters and a radius of 5. So right, so this arc length we now know, which is 13, radius of 5. We are asked to find the angle. So using our formula, the arc length is 13, the radius is 5. I'm going to multiply that by theta, so I'm simply going to divide. So 13 over 5 is equal to theta. And remember, this is in radians. Okay, so the answer that you get is going to be in radians. So this would be an exact value in radians or a decimal value in radians. And that is all for day 1.